Hello everyone, I'm Daniel O'Sullivan and I'm a new interviewer for the QBIN podcast. In this first interview, I had the pleasure of speaking with Mickael Tanter, whose pioneering work in ultrasonic imaging has made him well deserving of being this year's keynote Feindel lecturer. We spoke for almost an hour and discussed not only his work, but his philosophies as a researcher and his interests outside of the lab. I hope you enjoy. So, hello Mickael. Thank you very much for joining here on the QBIN podcast. So you're of course our keynote speaker for Feindel, and could you perhaps maybe give an overview of what it is that you do, perhaps, and if I could ask for you to maybe do it at two levels, one as though you're sort of speaking to the general public, and then maybe at a higher level for other experts in the field.
So hi, Daniel, and thank you very much for the interview. So I'm working mainly as a physicist. At the beginning of my career, I was really a physicist by nature. And I've been working a lot using waves, and especially ultrasonic waves. And as I was interested by medicine, I tried to apply the use and generation of ultrasonic waves to biomedical imaging and biomedical therapy. And the first part of my career, I've been working on trying to find ways to focus ultrasonic waves through the skull bone in order to do thermal ablation of tumors in the brain using what we call high-intensity focused ultrasound. And so I've been working on this during some years, but in parallel, I began to work in another field which was really interesting, which was to use ultrasound in order to do what we call ultra-fast ultrasound imaging. So instead of making an echographic device at typically 50 frames per second, so 50 frames per second, it's typically what we call real-time TV of our body, because our eyes are able to see at 50 frames per second. In my case, I was trying to make ultra-fast imaging with plane waves instead of focused beams in order to reach typically 10,000 frames per second. So we could ask ourselves why to do an ultra-fast scanner like this. And I wanted to make very fast images because I wanted to see vibrations that are inside our body. And these vibrations, we call these shear waves, shear mechanical waves, seismic waves, in fact. They propagate at a speed which is typically 1 meter per second, so quite fast. And if you want to see these waves inside our body, you need to make one image every millisecond, typically, in order to track the wave every millimeter. And in order to see these waves, we had to create this ultra-fast echographic device. And I was working on this because this shear wave is interesting because its speed is directly linked to stiffness. So if you've got access to this kind of waves inside our body, if you see this mechanical wave, you will have access to the stiffness of organs, and you will be able to make quantitative maps of the stiffness of organs. And so it was a kind of technology where we were creating a vibration remotely with ultrasound, what we call the remote palpation of organs with ultrasound. And then we were imaging at ultra-fast frame rate. And it was a kind of human body seismology, in fact. And when we did this, the goal was to provide quantitative map of stiffness of organs in color on an echographic device, on an ultra-fast echographic device, because in fact, stiffness is perhaps one of the most important parameters of medicine. It's what physicians try to measure when they do palpation. They try really to feel if there is a stiff lesion, for example, in breast, or a soft medium or stiff medium in liver. And we know that stiffness is very, very linked to pathology. As soon as you've got a pathology, your tissues are going to be modified. The architecture of tissues is modified. You've got fibrosis, for example, sometimes in the liver. When you've got a tumor, you've got a vascular system which is going to increase in one region. And so if you make a map of stiffness, you are going to improve the diagnosis of cancer. So it was perhaps 15 years of my career has been going from basic fundamental physics to biomechanics of the human body. And a little bit later, I began to use ultra-fast imaging with ultrasound in our body in order to see blood flow. In ultrasound, we are able to see how red blood cells are moving in our vascular system. It's what we call the Doppler effect. And we began to make a modality, we call this ultra-fast Doppler. And it was interesting because ultra-fast Doppler was able to see the vessels, but not the big vessels where you've got very fast flow. We were able to detect flow in small vessels. And so it was very sensitive to blood flow, much more sensitive than a conventional echographic device. And we were able to see blood flow in small vessels of about 200, 400 micrometer diameter. So when I understood that it was possible to see blood flow in such small vessels, I thought that perhaps we could do exactly like fMRI. You know, in functional MRI, you are able to see the activity of neurons in the brain just by studying how the oxygenation locally is changing or the blood flow is changing also. And in our case, in ultrasound, it was not possible to do this because, in fact, we were not able to see small vessels. But as soon as we invented ultra-fast Doppler imaging, we understood that we were going to be able to see these small vessels. And in these small vessels, there is a phenomenon that we call neurovascular coupling. It's very simple. In fact, when your neurons are working in one region of the brain, the blood flow is locally changing in the small vessels in order to feed the neurons to bring more nutrients to the neurons. And in fact, we began in 2011 to make experiments in rodents where we vibrate, for example, a whisker of a rat, because we know that there is a region of the brain, what we call the barrel cortex, where, in fact, if you've got a neuronal activity, there should be an increase of blood flow. And we measured this with ultrasound. It was really the first experiment where we were able, with ultrasound, to see neuronal activity, in fact. And it was interesting because ultrasound is a quite cheap technology. It was really easy to use, and the resolution and sensitivity was really very high compared to fMRI in rodents. So it was the introduction, in fact, of ultrasound in neuroscience. In fact, the beginning of ultrasound neuroimaging, and we pushed this field during the next 10 years, between 2010 and today. We have been working a lot on what we call neurofunctional ultrasound imaging for neuroscience and clinical applications. And in parallel of this, again, it was around 2010. It was good years for our research. I found a way to see the blood vessels, not the small vessels where we do neurovascular imaging, but even smaller ones. It was going down to capillary level, so really vessels that are about 10 micrometer diameter, for example. And this was complex because it was a little bit for a physicist, it was like a graal for research, because it was trying to be able to see at microscopic scale inside our body, but remotely from the surface. So when you think about the microscopic imaging, you think about a microscope, and microscope is optical imaging. And in fact, we know that we are able to make really beautiful images at the micron scale using optics, but it's only surface imaging. Otherwise, you have to put an optical fiber inside the medium. And in fact, with ultrasound, we found a way to go down to microscopy, but remotely from outside. And what we have to do, the trick is to inject intravenously. So in the vascular system, you inject a liquid that contains millions of very small microbubbles, gas microbubbles. And these gas microbubbles have a very small size, typically 1 micrometer. You inject them into the vascular system, and then you do ultra-fast imaging. So you see, it's again the same invention, ultra-fast imaging, that we use in order to image the motion in the medium. And if you do ultra-fast imaging, you are able to see very nicely the motion of microbubbles in your brain or in other organs in the vascular system. And you can localize one single microbubble with a much higher precision than in conventional ultrasound. So you increase the resolution by a factor 50 sometimes, and you go down to resolution of about 5 micrometer. So you are able to see the vascular system up to capillary level, but really fully non-invasively. And it was nice because it was the first time there is a modality which is able to see at microscopic scale the vascular system from outside, at whole brain scale, in fact. And it was possible even to quantify the hemodynamics in these small vessels because we can track the microbubble when it travels along the vascular tree, in fact. So we work a lot on this. It's what we call ultrasound localization microscopy. And we apply it to cancer imaging, to neuroscience also, because it's giving really very interesting information about the vascular system and the hemodynamics in the very small vessels. Yeah. So it's a kind of very short summary of what were really the most important steps in our research in my group. Yeah.
That's fascinating. That is really fascinating, especially being able to, measure such small, just neuroimaging on such a small scale, vascular imaging on such a small scale. That's very impressive. And I guess one of the first things that comes to mind for me is it not a headache to try and resolve like signal to noise ratio things, like issues like that come up when doing this? Yeah.
Yeah. In fact, there is a lot of tricks to use, but what is really nice is that as soon as you go ultra fast, as soon as you've got thousands of images per second, you really nicely see how the signature of microbubbles are moving inside your vessels. And you've got a huge amount of information. You've got a very large set of raw ultrasound data. And there is mathematical operations that you can use. For example, what we call, it's an ugly term, but it's what singular value decomposition of matrices. We can use this kind of techniques that makes that you can really discriminate what is really the signature of your microbubble. From you discriminate it from the background noise, from the noise coming from tissues, from blood flow, and you keep only the signature of microbubbles.
Cool. And is it any better, this sort of imaging, is it any better for, cortical as opposed to deeper subcortical regions or anything, or it can be used anywhere in the brain? Is there anything like that?
Yeah. In fact, what is cool also is that functional ultrasound. So functional ultrasound is what we use without microbubbles, and ultrasound localization microscopy is what we use with microbubbles. But even functional ultrasound is able to see the whole brain. So of course, in mice, it's transcranial because the skull bone is quite thin. So we are able to see the flow in the whole brain. Even below the brain, we are able to see the trigeminal ganglia. So it's really an imaging modality which is able to see extremely deep in the brain. And when you use microbubbles, it's the same. In fact, we made some years ago, 3 years ago, we made the proof of concept of ultrasound localization microscopy in humans by using microbubbles, and we do imaging through the temple windows because it's a place in the skull bone where the skull bone is a little bit thinner, so we are able to have a nice signal to noise ratio. And in that case, you can see the whole brain. So it's only 2D imaging at that time, but we see deep up to 15 centimeter deep at microscopic scale.
Wow. What would you say has been some of the most challenging, some of the most challenging aspects of doing this research? Was there anything in particular that stands out to you?
In fact, at the beginning, it was prove the concepts because of ultra fast imaging, because we had to really to prove that we were able to image at thousands of frames per second. So the development of this technique was quite complex, and especially because when we began to work in that field and prove the concepts, the technology was not evolved enough in order to be able to calculate the data in real time, in fact. So when we were acquiring, it's a funny story, when we were acquiring 0.5 second at ultra fast frame rate, it was taking us 1 hour of calculation just to make this 0.5 second movie. So some people in our community were saying it's not an ultra fast system you are building, it's an ultra slow system. But in fact, we were excited by this because we were proving the concept. And after that, we just use the evolution of Moore's law, the exponential increase of the computational power that was proposed by Gordon Moore, the CEO of Intel. In fact, we just use the fact that every year there was a 2 times faster computer, and in 10 years, it became possible to calculate the data for a 0.5 second movie. It was possible to calculate in 0.2 seconds instead of 1 hour. And it became possible to do a fully software-based echographic device, ultra-fast echographic device, with GPU boards. So the GPU boards you've got today in your computers. And so this period was quite challenging because we were proving for the first time new concepts, and we were trying to implement it fast enough so that we can have on an echographic device an ultra-fast acquisition, imaging of vibration, and at the same time the production of a stiffness map for the doctor, but in real time. So we had 2 or 3 images of stiffness, quantitative maps of stiffness per second, and for the physician. So it doesn't change anything to the echographic exam, but you are adding a really important and quantitative information about the mechanical properties of tissues. And then what has been complex is in the field of neuroimaging, it has been to really prove and to convince people in neuroscience that functional ultrasound was an interesting modality, because when you introduce a new modality in a new field, in a very large field, neuroscience is a very, very large scientific field. There is a lot of modalities that are present, and you have to progressively try to convince that the new modality you propose is going to give information that the other modalities are not able to give, in fact. And it will be, of course, it's not, we don't want to make something which is completely in competition with other modalities, but we have to prove that there is something which is complementary to the other modalities, that you can combine with them, but you can really grab data and grab information about, for example, neuronal activities that is going to be really interesting compared to the other modalities.
Cool. Now, you're very much on the imaging side of things, it sounds like. Have you ever dabbled at all in the modulation side of imaging as well? Yeah.
In fact, I've been working in 3 different therapeutic applications. At the beginning of my career, I was working with what we call high-intensity focused ultrasound. So we were sending ultrasonic beams through the skull bone in order to burn tissues, so really to burn small lesions in the brain. And after some time, I moved to imaging. But in around 2010, we came back, or 2005, between 2005 and 2010, I came back to the field of therapeutic applications of ultrasound with one of my colleagues, Mathieu Pernaut, and we had a crazy idea. It was to use ultrasound for very high amplitude pressure pulses, so for what we call histotripsy. We wanted to use shock waves, very, very focused shock waves, in order to break calcifications inside cardiac valves. So our goal was really to send ultrasonic waves through the ribs in order to focus on the cardiac valves. When patients become older and older, many people have problems with their valves, so they have calcifications, and the valve becomes very stiff, in fact. And it's a kind of, the aortic valve is a door. In fact, it's a door that is opening at every cardiac cycle and sending the blood flow in all your organs. So here the door is very stiff, and it's very complex to open the door. And the patients are really have to work a lot in order to make that their cardiac muscle is contracting a lot in order to send the blood flow everywhere in their organs. So today, in order to treat these patients, what we have to do is cardiac surgery. So you have to to do open chest surgery, you have to replace the valve by a bioprosthesis. Or there is another treatment which is called TAVI. It's a treatment where you've got a system which is going through inside the femoral artery, going up into the ventricle, going up to the cardiac valve, and there it expands the intraventricular tool is going to expand bioprosthesis. But it's quite very complex surgery. It's invasive, of course, and the surgery is so complex and risky that people wait that the disease is progressing up to a point that you really have to make surgery. And our crazy idea was to try to say, okay, with ultrasound, we are going to be able to image the valve with a conventional echocardiography imaging. But at the same time, with our device, we are going to focus a shock wave on the valve to target the valve. And there we are going to break calcifications inside the valve in order to soften the valve, in fact. And as soon as the calcifications are fractionated or broken inside the valve, in fact, your valve becomes softer and the door opens more nicely. And we made 100 patients. So we created a startup company with Mathieu, and this startup company was called CardiaWave, and CardiaWave has been making the first fully non-invasive treatment of cardiac valves in humans in the last years. So there is now more than 100 patients, and they are going to be CE marked soon. So it's really, I think it's really a fantastic technology, because it's opening the way to fully non-invasive treatment of cardiac valves in humans. So it was one with, you see, shock waves, mechanical waves. And more recently, with my colleague Jean-François Aubry, we've been working with, again, in the brain now. So we send ultrasonic waves through the skull bone in the brain of patients in order to neuromodulate the activity in regions. So it's the concept of ultrasonic neuromodulation. So we send waves that are low frequency, low intensity. There is no destruction of tissues. We just want to inhibit or stimulate regions of the brain, in fact. And in our case, currently we are working on severe depression patients. So we made a system which is already currently in clinics for clinical evaluation and clinical validation. And our goal is to really to make the treatment of psychiatric disease, so severe depression, addiction, with ultrasound, non-invasive ultrasound neuromodulation.
And is this, again, with this sort of these neuromodulation techniques using ultrasound, how easy is it to target specific brain regions? Are there some regions of the brain that are typically very difficult to reach? Are there some that are easier to reach, that sort of thing?
Yeah, it's an excellent question. In fact, one of the problems of neuromodulation through the skull bone is that the wave field, in fact, when it passes through the skull bone, it is distorted, because the speed of ultrasound, the speed of sound in the skull bone is very different compared to the speed of sound in soft tissues in the brain. So in fact, it's a kind of diffracting medium, the skull bone, or aberrating medium for the wave. So usually, in order to correct these aberrations, what we use is very large arrays of elements. So you've got plenty of small ultrasonic transmitters, and we are going to change the time delays on each element of the array in order to create a kind of distorted wave, but we shape this distorted wave so that when it passes through the skull bone, it corrects the aberrations of the skull bone in order to recreate a spherical wave after passing through the skull bone. It's what we call adaptive focusing, and we have to adapt the focusing to each patient, because each patient has a completely different skull bone, in fact. And we worked a lot with Jean-François Aubry in the last 20 years on this. I made my PhD in 96 to 98 on this, on the concept of correcting these aberrations. And what we do is we use a CT scan of the patient, so we know the structure of the bone of the patient. And then from this, we can also use an MRI system with what we call UTE sequences, ultra short sequences. And in fact, we have access to the structure of the bone, and we can really know what should be the perfect shape of the wave to send through the skull bone in order to correct the aberration. And in the past, and a lot of people are using very large elements, very large arrays made of thousands of elements or hundreds of elements, where they shape the wave field like this. But it's very complex electronics, very complex probes, because you've got hundreds of elements. And in fact, we found a much easier way. It's a nice trick. What we do is we have only one element, one array, which is a spherical array. And instead of having a lot of electronics behind, what we do is we calculate the shape that should be placed just in front of the probe in order to correct the aberration. And we print it in 3D, in fact. So we create a material, which is a kind of lens, a meta lens, which is correcting the aberration of the patient. And with this meta lens, it becomes very easy to focus even complex beams through the skull bone of patients and to go exactly at the location where we want to focus. And in our case, in the treatment of psychiatric disease, what we want is we want to target the very deep regions of the brain. In fact, we want to target, for example, for severe depression, we target the intersection between different fibers in the brain and in the SGACC, so the anterior cingulate cortex, which is quite deep in the brain. And it's really an advantage of ultrasound. Ultrasound is able to go very deep in the brain. And in these deep regions, the resolution of the focal spot is about 1.5 millimeter by 2 millimeters by 1 centimeter. So it's a large rice grain, in fact, that you are going to stimulate.
Wow, wow, that's truly fascinating. Honestly, sounds like such an enticing field to me. I'm wondering, sounds like you've really touched on just about every kind of corner of ultrasound technology and medical field of medical science that I can really think of. Would you say that of the research that you've done, would you say that your best known or best recognized research is the same as the research that you're most proud of, or would you say there have been other maybe side projects or passion projects that you do on weekends or something that you're more interested in?
It's strange because at the beginning of my career, I was pushing hard, and I have been pushing hard the people in my team to go from science, fundamental science or applied science to applications. I really wanted that what we do in the lab is going to have applications and go on to patients and save patients or make a better diagnosis or make a better treatment. So I was pushing a lot to go into clinics and from our research, and we were creating startup companies that have been growing since that time. So, and I've been really eager to prove that what we were doing was really interesting for patients and that it was working, which is complex because when you go from basic physics up to prototypes and then to clinical evaluation and prove that the technology works, it takes 20 years to make the full pass, in fact. But in the last years, till perhaps 10 years, I began to like to work also in fundamental science and come back to fundamental science. And the older I'm becoming, I think the older the more I try to go back to fundamental science. And currently, I can give you two examples that are works that I love a lot and I was proud of. Very recently, we made a paper with one of my PhD students, Jérôme Barangier. He's a great student. We've been working on the way we measure tension. So when you try to measure your blood tension, you use a cuff and you are going to compress your arm and you compress your artery in the arm. And in fact, to measure tension, systems and physicians are listening to sound, what we call Korotkov sounds. And in fact, this sound, they are created when you reach the systolic pressure and the diastolic pressure. Between the systolic and diastolic pressure compression on the cuff, you hear this sound. And in fact, these sounds were discovered by Korotkov. It was a Russian physician in beginning of the 20th century. And I've seen that in the last centuries, there has been a lot of hypotheses to explain what was the Korotkov noise and Korotkov sounds. But in fact, all these explanations were not true. In fact, there was a lot of false hypotheses. And in fact, in the last years, we've been using ultra-fast imaging, to image the vibrations that are propagating under the cuff in your arm when we try to measure tension. And we have been explaining what are the Korotkov sounds. In fact, it's vibration in the arteries, which are creating shear displacement in tissues, and these shear displacement are propagating up to the stethoscope, and they create a sound just at the surface of the stethoscope. So in fact, Korotkov sounds are not sound; it's shear waves that are creating a sound just in the stethoscope. And we made the theory of the propagation of this wave, and in fact, I like a lot this work because it has no application today. Perhaps later it will have one, but in fact, it was just trying to explain a phenomenon which was not explained, and a phenomenon which is used every day in all hospitals, in all medical practitioners is taking your blood tension every day, and this was not explained. In fact, so it was we were really proud of this and happy with this. And there is another topic. I'm working for more than 6 years now on sleep. And sleep is so important. It's one third of our life, and we struggle to try to understand really why we sleep. And there is a huge amount of people working in that field. And in the last years, I've been using ultrasound in order to better understand what we call the REM sleep, the rapid eye movement sleep. And we've been imaging in rodents the change of blood flow during non-REM sleep and REM sleep, and we've seen that there is huge vascular waves with increase of blood flow of about almost 200% increase of blood flow during REM sleep. So our brain is working like crazy during REM sleep, and currently we try to explain why nature made that the metabolic consumption of our brain is so huge during REM sleep. So it's one of my favorite hobby. So it's a side project, but perhaps it's the one which I love the more. I like the more.
So I was wondering, perhaps I might switch to some bigger picture questions about research. What do you think, in your own opinion, makes worthwhile research? And I know that's a big question, but some things in your opinion.
I think really when you do research, you are so lucky because you are just in front of the what is invisible, what nobody knows. In fact, you try to push the boundaries of human knowledge. And in fact, it's something which is sometimes frightening for people, but also extremely exciting. In fact. And very often I say to my PhD students that of course the PhD life is not something which is quite smooth. In fact, sometimes you are depressed because nothing is moving, and you try to solve something, and it takes time, a very long time. But when it works, when it begins to work, the reward is fantastic. In fact, because you've been suffering a little bit in order to get to that point, and it works. And then again, you've got as soon as the reward has come, you have to continue to progress. But it's giving you sometimes the most extraordinary reward, in fact, because you understand things. And very often I'm thinking about my parents. I thank them so much to have helped me to work in school and be able to work in science, because science is extremely rewarding, because you are able to look at nature, in fact try to look at nature, but to understand, try to understand it with concepts that that you are able to understand. If you have some mathematical tools, if you've got some equations or physics tools, you you are able perhaps to better understand the beauty of nature and the beauty of concepts. Sometimes you have to learn a lot of things in order just to appreciate and the beauty of simple things, in fact. So to understand simple things is the most complex thing, and and making things simple require to go through a very long process, but it's a process which is rewarding, and especially if you do it as a team, in fact. So doing it alone is not very interesting. What is fantastic for me when I'm coming every morning in the lab, I'm really happy to come working every day, and it's something that it's really important in life. If you are happy to come to work and work with people, it's fantastic. All the discoveries I made and all the concept we proved. In fact, the most exciting part was when we were doing it as a team and we were several ones on the looking into the data, doing the experiment and say, yeah, yes, it works. But it's it's a common work, in fact. So a teamwork, uh, and the fact that you've got the chance to understand concepts that are that are beautiful in nature, I think.
Good. Yeah, yeah, yeah.
And also perhaps a transmission also of knowledge. In fact, mentoring people, teaching to people, and then you know perhaps the thing I'm the most proud is all the students I had, and to see that many of them have been staying in research and continuing in this field. And I have a very good friend, James Greenleaf. It's a fantastic professor from Duke University, Duke Mayo Clinic, and he was one day he told me we recognize a great scientist not to what he has been doing, but to what his students have been doing. And I think it's really a good definition of a good scientist. If your former students make great work, in fact, it's, a, the fact that you've been helping them in the good way.
For sure, for sure. On that topic of teamwork, could you perhaps speak to how you feel the labs that you have been in have perhaps to what extent they've shaped you as a researcher, or perhaps on the inverse of that, how you have shaped the labs that you've been in?
Yeah, in fact, I've been really lucky because after I did my PhD, I received a permanent position at in France at CNRS and then at INSERM, so the French NIH, but very rapidly. In fact, 10 months after my PhD, so it was I was really lucky, and I was also lucky because it was. Uh, so our lab was beginning to work on biomedical applications. So it was really the seed of something that was going to grow, and it was my responsibility to make it grow. In fact, so in fact, I've been lucky because each time I had a very good student. And in fact, it was possible. He was applying to the positions in France, and a lot of my former students have received a position, and they stayed in my team, in fact, and the lab grew. So we were when I were in the beginning of 2000, we were 3 or 4 in the team, and now we are 80 people. And each, of course, each permanent researcher now has his own field, but we continue to work together, and which is really, really, I think, a little bit special, and it's possible in the French system of science. It's not possible everywhere, but it's really, really extremely interesting because people have their own topics. They are responsible of their projects, of course, but we continue all these permanent researchers. We continue to work together, and the PhDs are working together also, and. So I try to shape the lab like this, so making that people have their own secret garden for research where they can evolve and be responsible of their part on their projects and so on, but try to make that they don't stay too much in the secret garden alone, but they work together and they exchange, they share, and it's working really like crazy in the lab, and I think people are happy with this, and there is a great atmosphere, I think, in the lab. So I've known only this because as the lab was growing fast and we were pushing hard on the topics, I was not able to leave. In fact, the first time I left my lab was only 1 year and a half ago. I spent several months in Caltech University in the States, but it was the first time I was leaving my lab after 20 years. 20 years.
Wow. Wow. You mentioned, some sort of relationships there that you've built with colleagues that you feel are somewhat unique to the sort of French research atmosphere. Do you feel like there's anything in particular that stands out to you as being unique to being a researcher in France as opposed to perhaps anywhere else in the EU, in the world, anything for that matter, or it's kind of the same across the world?
Yeah, there is not something really completely different from the other countries. Uh, what is nice in the French system is that it's possible to have several permanent researchers in the same lab. So, for example, in the United States, it's the lab is really, there is a PI, there is students and postdocs and some engineers, but there is not the possibility in a big lab to have a lot of different permanent researchers working in their field, in fact. So structurally, it's possible in France to do this, to have big labs with each permanent researcher having his own field, but working together. So I think it's possible, but people have to be keen to do this. So you have to create a culture in a lab, and so try to make this kind of culture. And in fact, in our lab, what we do is, of course, every PI has his own topics and where he's responsible but in fact we share a lot of things. In fact, we share a lot of our machines, we share our ultrasonic probes, we share our devices, all our devices, and if one researcher sometimes has problems of money 1 year, the other ones are helping him. So it's making stronger as a team. In fact, I think we can help each other like this. Yeah.
Sounds, yeah,
But
sounds,
it's
yeah. Go ahead, sorry.
yeah, but I think, yeah, sorry, I think it's not the same everywhere in France. So you have to have the possibility to do it from your institution, but in your system, national system, which is possible in France. But you have also to push this kind of culture, which is not the same in all the French labs.
Mm. Yeah, I was going to say it sounds conducive to sort of a collaborative spirit, that sort of thing, where you can have multiple people all sharing and sort of working together at the same level in a lab like that. Right. So I suppose another sort of big question for you, would you have any particular advice to a junior researcher that's just starting out in the field, from your own experience, but from what you've seen and so on?
Yeah. One of my advice would be first of all to not to share, to try to share at maximum. So people really very often they work as small groups, very on their own topic without sharing with the other ones. And if you are not completely open with the other ones, in fact, you are missing opportunities. In fact, so I always say it's better to have two papers, one where you are first author, one where you are second author, for example, and the other PhD student will have one and the opposite. So you will have both, you will have two papers, in fact. And the two papers will be better because you have own expertise, different expertise, and you are going to share it. So if we are smart enough, we can increase the number of papers we do and we increase the number of good science we do by sharing part of what we do. But of course, we have to make that everybody is happy with this. And so I would say try to share, because when you share, you receive a lot also. So sharing is receiving, I think. So So sometimes it's counterintuitive. We have the feeling that the science is very, very competitive, but my feeling is that sharing and collaborating is making you more competitive, because you will have what you would do alone, but you will have more, because you will be associated to the work of the other ones, and they will help you on your own work. So I would say this. So really share, and collaborate. And of course, you have to think of your career at the beginning of your career. It's complex to find positions, and you have a lot of there is pressure for results, but sharing is receiving also. I'm sure about this, and it's something I've been feeling all my career. And I see also that the young researchers that were working with me, they have been progressing faster thanks to this, in fact. And it's something I've been seeing a lot in the generation of students I've been teaching here. The second thing I would say is don't forget to what is the most important part of what you do is science. And so it's great to find money. We have to apply for grants. We have to find grants, but it's not the most important. And I remember people, so young people that received the position, they were searching for a lot of grants and trying to have grants, and sometimes it was not working, and they were struggling. Application after application, and doing this during 2 or 3 years. But when you do this all the time, you don't have time to do science. And so we should keep in mind that the most important part is science at the beginning of the career. So sometimes with not so much money, you can do good science at the beginning. And when the science is good, after it helps you a lot to find the money. But you should begin with science, and science is going to help you to find that money to expand what you are doing. But our international system and the way scientific system worldwide is done now is making that sometimes young researchers, they do the opposite. They are enforced to do the opposite. They are thinking that they should try to find a lot of money before doing science. It's not, no, it's science which is the driving force. And as soon as the science is good, you will find the money. Yeah.
Mm. Cool. Now, was another sort of big question, was medical physics always the field that you were, that you felt you were destined to end up in, or was there a crossroads at some point? Were you going to go in to become a painter at some other point, earlier in your career or something like that? Was there anything else on the horizon?
Yeah, no, well, no. In fact, when I was young, I was fascinated by the human body. I wanted to work in that field. I wanted to be a physician. In fact, when I was young, but my parents and my professors at school, they were saying, "Oh no, you are great in mathematics and physics. You should do mathematics and physics." So, as I was young, I listened carefully to what they were saying, and I went into the field of science, physics, and so on. And I love it. Really, today I love it. But in fact, when I began to work in physics, I was continuing to think about the human body and nature and so on. And I tried to 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 change the curvature of my path, my direction, to make that my physics was going to be applied in medicine or biomedical field. So it was a lot of hazard, but at the end, when I look back, I'm doing what I was good at, and for what I was loving. So and now it's I've got a funny story to tell you. One day I was with one of my I don't know if you can you hear me?
Yeah.
Okay. One day, I've got a small and funny story to tell you. I was with one of my colleague and a friend. It was a neurosurgeon. He was doing surgery, and I was doing imaging during surgery. And I was really fascinated by this surgeon. He was like God for me, because he was he was doing some stimulation in different regions of the brain. I was able to see the brain in action directly on humans, like in the operating room. And I was telling him, "Oh, I'm completely fascinated. It's fantastic what you do. Your job is amazing." And my friend, he was telling me, "Oh, but no, Michael, in fact, it's really my job is really boring. I'm doing this almost every day." And you cannot imagine. You are the lucky guy because you are doing physics. But today you are with me working in neuroscience, but tomorrow you will be working with cardiologists. Then you will be working with guys in cancer, doing imaging, doing therapeutic device. So you change every day. So you are much more lucky than me. And I keep this anecdote. And it's true that today I found that it was not a bad choice to choose physics and then to apply it to medicine.
Yeah, that is nice.
But I didn't know it. Yeah, but really, I didn't know it when I was 20 or even 25, 30. Even when I was 30, I didn't know this. I know it today, but
yeah.
yeah.
It's nice that you get that exposure to just a whole host of different fields within, medicine, because really imaging can be done anywhere in the body, right? And, that's really nice. I suppose in many ways, it's that early idea that you had of becoming a physician, you get a taste of every sort of possible physician that you could have been, it's like doing
Yeah.
cardiology, as you said, or doing, neuroscience stuff or anything for that matter. Yeah, very cool, very cool. Um, so outside of research, do you have any particular interests? Are you big into music or arts or cuisine or anything like that?
Ah, yeah, in fact, I like doing sport. I've got two boys, two children. In fact, they are bigger than me now. They are 20 and 18, but we do a lot of sport together. And I like swimming. I've been swimming when I was young, and I continue to swim. In fact, it's two times, 3 times a week. I love to do everything which is around the sea. So diving, uh, swimming. So I love this. In fact, my parents are living in a small city in the west of France, just in front of the sea, and I've been spending all my childhood just in front of the sea. So it's very important for me. So each time I go there, it's like a drug. In fact, if I don't see the sea during several months, I become more crazy. So I've got to go to see the sea.
Nice, nice. You said in the west of France. I saw on your Wikipedia. Now, correct me if I'm wrong, but you grew up in Paimpol, if I'm
Yeah,
pronouncing,
yeah, yeah,
which is in
yeah.
Brittany. Did you ever learn to speak any Breton growing up as a kid, or no?
Yeah, I know some words. I understand some sentences, but I don't speak Britain. I know some bad words.
Oh yeah.
But you
Cool.
see, in there is people in the West of Brittany don't speak the same language as the ones in the south of Brittany. So there is a lot of differences. Even my parents, when were speaking with the grandparents, they were from two regions of Brittany. They were not understanding everything that the other ones were saying. So.
Cool. Cool. Um, Another question, if you had to grab a beer or a coffee or something like that with any intellectual throughout, I might ask first French history, but then perhaps history just globally. So in France, anyone from Descartes to Laplace to Camus, you name it. Who would you choose and why?
Wow, wow, very complex question. Uh, if I give you a word, a name, in fact, I'm going to regret it because I will say 5 minutes later, oh, I should have chosen this one.
Perhaps
Uh,
honorable mentions, maybe not the best one, but someone who's up there.
mm, it's, Yeah, perhaps I would choose Jules Verne. You know Jules Verne. He
Oh
was
yeah,
he was
yeah,
a
yeah.
writer in the end of 19th century, and he was in advance. He was one of the first science fiction writer, and he's been fascinating. When I was a kid, I was reading all these books of Jules Verne, and I was always fascinated. I think it's part of my envy to become a physicist came from this, in fact, from Jules Verne. So I would say perhaps Jules Verne, and perhaps another one. And yeah, if I could speak with somebody perhaps it's also David Gilmour in music from Pink Floyd. I would love
Okay,
to
okay.
speak with this guy because yeah, I'm fascinated by his music.
Are you a big you're a big Pink Floyd fan then, I guess, are you?
Yeah,
Yeah,
yeah, yeah,
yeah.
yes, it's true.
Cool, cool, cool. So I'll end on a final question. I mean, from all that you've told me, I think it's pretty clear what some of what part of the answer to this question will be. I mean, you've done a lot of really truly groundbreaking, very impressive work. What do you hope will be the legacy of you, Mickael Tanter, for the field of science, or perhaps life in general?
Wow, I don't know. I don't know. It will not be my own legacy. In fact, it would be. I'm sure it would be the legacy of my team. It's a teamwork. So legacy. It's something I'm cautious because very often we say we present and people like to have one scientist that say, okay, been doing a lot of discoveries. In fact, I did this with my team as a team, but yeah, what I would love to for the community to keep is I think yeah, ultra fast imaging, of course. I would neurofunctional ultrasound, ultrasound in neuroscience, and also microscopy. I would love to people to keep this in mind. So the three main things were this ultra-fast imaging, neurofunctional ultrasound, and ultrasound localization microscopy. And perhaps I hope in soon something on sleep. I'm working a lot
I
on sleep, so I hope they will keep something on sleep.
Nice. Well, there's certainly a lot there, and it's been an absolute pleasure getting to talk to you and getting to hear all of your
It was
contributions. And I'm very excited to see you here in May when you come to give your keynote lecture.
Yeah, thank you so much, Daniel. It was great to discuss with you, and I thank you very much for your warm welcome in your country soon. So thank you so much.
Okay, thank you. Have a good day.
Bye. Bye. Have a good day. Thanks.